write the equation and sketch the function with each of the following properties. Whole at x is equal to, draw any graph. Okay, so I can draw a line like this, and I want to hold it. So basically, listen, I'll tell you. Right? If there's a whole at x is equal to 2, now what is the equation of this line?
Y is equal to x.
Y is equal to x. If there's a whole at x is equal to 2, that means your x minus 2 is cancelled out.
Right.
So your y is equal to x square minus 2x upon x minus 2.
Oh.
With the x minus 2 is cancelled out. And you draw simplest one y is equal to x I did. And then multiply and divide by x minus 2. Again, not therefore I mean.
So your denominator has to be x minus 2.
Correct. So x is equal to the denominator will be x minus 2. So what is the simplest one? Fx is equal to x upon x minus 2. So horizontal asymptote. How do you find the x-intercept and the y-intercept? Suppose you put x as 0, y will be minus half. No, x is 0, y will be 0.
So because that is the equation, no? The equation of the line is y is equal to x only, no?
No, but you have to sketch a graph. Suppose, so how will you sketch this graph? Suppose if I give you.
Wouldn't it just be like that and then stop at the vertical asymptote?
No. It won't. No, this is different. Okay. You see this. You have to again those 4-point thing. Get your x-intercept, your y-intercept.
So my x-intercept will be
so your what's your horizontal asymptote? Y is equal to 1.
Yeah.
What's your y-intercept?
So my x is 0, so 0.0.
So it will pass through 0. Yeah. Pass the 0 minus 2, no? So it will pass through the origin like this.
So 0 minus 2 is not defined.
No, 0.
Is it?
Yeah. 0.0 is not defined. 0 a number is 0. So your horizontal asymptote is y is equal to 1. This is x is equal to 2. So that's a vertical asymptote. Means the derivative at x is equal to 2 is not there. Next.
So now from the positive side, y is 3.
The limit is 3. It's approaching 3. So 2 from the positive side is 3. Correct? It's approaching 3. Basically here. And 2 from the negative side is approaching 0. So basically I'm drawing any shape, doesn't matter. Here.
And so there will be a hole because
it's not defined. Yeah, at 2 it's not defined. Both they have 2 holes.
But the function will be defined somewhere else on
yeah.
right?
Yeah. Maybe not. It may not be defined.
At all?
At all.
So I
It's okay.
just have 2 holes in the middle.
Yeah. Why? There's no rule like that.
Oh yeah, like in the first
there's no rule like that. There's no rule per se. For each of the above examples, state the limit as x tends to 2 and explain why it doesn't exist. In the first one, does the limit exist?
No, sir. Because it's different
from first one.
Left and right side.
Left hand limit is what?
2. Oh, even right is 2.
So exists. Because left hand limit and right hand limit are 2. So you can say limit as x tends to 2 plus of the function is 2. And limit as x tends to 2 minus of the function is 2. Okay. Then?
So next one, it doesn't exist.
Doesn't exist.
Yeah,
because it's negative infinity. Yeah. So limit as x tends to 2 from the positive side of the function is going to plus infinity, and limit as x tends to 2 from the negative side of the fx is going to minus infinity. So it doesn't exist. Then?
So next one, it exists.
Doesn't exist.
Oh, because yeah, I have a
It's not
hole,
the
sorry.
same, no?
I
It's
have a
not the
hole,
same.
I have a hole.
This is 3 and this is 0. This and this should be the same. Left hand limit and right hand limit should be the same.
Oh. And so if the minute I have a hole, it means I can't, it doesn't exist,
It
right?
doesn't exist. The limit can exist, even if the hole is there.
Even if there's a hole, you can have a limit.
You know, first one, the limit exists.
Oh yeah.
Even the hole is there, the limit exists.
So even if it's two
Yes,
holes like
yeah,
that,
yeah.
a gap in the middle,
No, there should not be gap. They
it
should
has to
be
be
the same.
continuous.
Not continuous, there can be a hole like this.
Okay.
This is not continuous, but the limit exists.
There's two types.
Yeah. Notes, discontinuous are classified into two different ways. Graphs 1A, 1B, 1C have point discontinuity and infinite discontinuity and a jump discontinuity. So this is your point discontinuity.
Okay. Yeah.
Infinite discontinuity.
We did this last.
Yeah,
last
and jump
session, right?
discontinuity. Yeah, jump discontinuity.
And we have to know these.
A
right?
point discontinuity is a removable discontinuity. So this can be removed by defining at this, you'd say at x is equal to y is 2. These are non-removable.
Which is so if you have to define
Remove
the
this.
hole, how do you do it?
F2 is equal to 2.
Or you just write that down.
Yeah. But this hole is, I'm plugging this hole.
Got it. So
One point you're allowed to put in. You can't put in infinite points in between. So identify and classify the points of discontinuity in each of the following functions. You may need to graph this. Yeah, obviously. Graph it and you see.
Yeah.
So if you put infinite discontinuity and x is equal to 3, if you graph it. Next one also you have to graph this. The example from the first page also leads us to a formal definition of continuity. A function y is equal to fx is continuous at x is equal to a if and only if the right hand limit is equal to the left hand limit is equal to the value at that point. All three have to be equal. See, for limit only this was there. For limit to exist, this was the only condition. For continuity, there's an additional condition. It has to be equal to the value at that point. There should not be any hole.
Also, for a limit, you only have to have your limit from both sides have to be equal.
Equal. For limit only this much was there.
For it to be
This
for
is
the
limit
to exist and for it to be continuous, you have to have this also. Okay. But so the derivative can exist regardless.
That is a different case. We'll come to that later. We'll come to that.
It is again a little confusing with the number of ifs and buts. And
Yeah. But that's what it is.
So is there a place I can find like a summary of everything, every single rule?
A function is continuous if it is continuous for all values of x.
Okay, so you can't have a hole.
Oh, you can't have a hole, you can't have an infinite discontinuity, you can't have a jump discontinuity. Use limit notation to explain when a function has a removable discontinuity.
So what do you mean limit notation?
Limit notation, this is a limit notation.
So f of a is undefined, is f of a is 0 plus 0.
Yeah, so that means when your limit as x tends to a plus fx is equal to the limit should exist.
Yeah.
The limit should exist and this is not equal to f of a.
Oh. Okay, so my limit from both sides is equal.
Like the first graph that we did.
But I just don't have this thing. I just don't have.
You don't have a hole.
Okay. I have a hole.
You have a hole, and to remove it, you plug the hole basically.
So where can I find a summary of all this?
No way. Okay. Find a value of a such that the piecewise function fx is equal to 2x plus 3. So left hand limit. Now how do you find a left hand limit? Limit as x tends to 2 from the left hand side of the function. Means anything less than 2. So this is my left hand limit. I have to use this function. That is limit as x tends to 2 from the left hand side means 2. Limit by substitution 2 into 2 plus 3. Correct? This is my left hand limit. Okay. Now I'll do my right hand limit. Limit as x tends to 2 plus. Right hand limit may this greater than 2.
So ax plus.
Limit as x tends to 2 plus of ax plus 1. So that would be what? a into 2 plus 1, limit by substitution, 2a plus 1.
And 7 is
Now,
equal to
third
f
thing, listen, we can do that, but you want to finish it. And also f2.
is equal to 2.
F2, now which one will you use for F2?
You can use the second one.
First one, equal to is here.
Oh yeah, okay, so
Equal to is there. So 2 into 2 plus 3, that's 7. So this is my left hand limit.
So 7 is
This is my right hand limit.
And all three have to be equal.
All three have to be equal. So it follows that 2a plus 1 is equal to 7. 2a is equal to 6. So a is equal to 2. So limit, continuity, now differentiability. Three things, three concepts.
Okay.
A function is differentiable at x is equal to a if the derivative exists.
It always exists.
No. No. Intuitively, a function is differentiable at x is equal to a if it is smooth there. It has to be smooth. It cannot be a cusp. It cannot be a to give you an example of what is not a derivative. See, listen. Modulus function y is equal to mod x. Y is equal to mod x.
Yeah.
Does the derivative exist at 0? Yeah. Does derivative exist at 0?
No, sir.
No. Why? It's a sharp point.
Oh, so it can't be any turning point basically.
No, I'm not saying turning point. Turning point it is. This is the derivative exist. Sharp point. Any sharp point derivative does not exist. If you have a cusp like this, the derivative does not exist.
So when any like
curve, smooth. It has to be smooth there. Like
so straight line isn't smooth basically.
no, here is the point. No? It's forming a point. It's forming a vertex.
Oh, so
derivative
is a point form. It's not smooth.
It is a curve. Like your y is equal to.
So parabola would have one.
Okay, but y is equal to x cube.
That would have one.
That will have one.
Even a parabola would have one.
Parabola has one. No sharp points. So cusp doesn't exist. This end point doesn't exist. Acha. At the end point also derivative doesn't exist. Like at this point, derivative doesn't exist.
Okay, because it's a point.
Point, it's just a point. It has to be a curve. Does it make sense to talk about f-2 for any of the example in question 1? Here. Will the derivative exist here?
Yes, sir.
There's a hole. Like suppose if you don't plug the hole, the derivative won't exist.
Okay. Because it's a point.
You also won't exist.
Yeah.
You also won't exist.
Yeah, because it's a hole. It's
So,
an edge point.
Yeah.
Okay. So it doesn't exist in holes. It in holes.
So for derivative to exist, the function has to be continuous. For derivative to exist, the function has to be continuous. Is one of the conditions.